This is actually like a multi-place topic. I'm covering loads and loads and loads of stuff, but we're going to be looking at a range of topics using a unifying method. So that might be useful. You can watch me model it. I'm going to try and model it exactly as I model it in class. But obviously I'll be messier because I'm using my Wacom, and I'll be quicker. So the first question is, what single skill in year 10 is a good indicator on higher paper being accessible? Lots of solving equations, and in particular algebraic equations. And I think that is the key indicator as to if somebody's capable of higher GCSE. I think higher GCSE is really hard if somebody can't solve equations like this. And I personally would devote as long as is needed in our school at making sure people can solve equations before moving on, because so many topics will be unpleasant. So just to show how we do this method of cross multiply. I do it waving my arms in the air, and I show them that they can do one side, they can do the other side, they can flip them both. But generally speaking, an equation like this, the next line should be 13x is 26 times 6. And I'd really encourage that, and I encourage them not to work that out on the right side. Most of what I do today is non-calculator methods. We divide both sides by 13, and then you can see why the 26 times 6 wasn't a good idea to work out. We can see that cancels with 2, so we get our answer of 12. And you know, we in year 8 we put that unknown in lots of different places, and we make the unknown linear factors, and sometimes we might even string together a like this one down here, a cubic equation or a very simple quadratic equation. But you know, all of that is really good for their algebra. And when they can do that, and when we are confident they can do that, we can start to think about ratio problems. Now, when I taught this before, I actually used to hate currency and most ratio things. It was the new GCSE that kind of made me think about it more. I always felt that students didn't know whether to times or divide by the multiplier, and I felt I needed to think about it as well. So now I've got a way that is fail-safe in their margin, in their books, or on the exam paper at the left-hand side. They just make sure that they get their numerators and their denominators the right way round, and it doesn't matter which way round it goes, is equal to how many pounds can I get for 36 of the dollars were at the denominator, 36x. So now we solve that equation. Better mathematicians will just bring the 36 up, but especially at the beginning of year 8 when they do, I do encourage them to actually do that cross multiplication, and the better mathematicians just get better when the time comes. So we've got our x is 360 over 18. Divide by x equals 20, and we write our comment at the bottom. So we were doing that in year 8, and I would promote that method for doing it after algebraic fractions. And we could do lots of different kind of practice of the same skill, which is all just practice of their algebra. 200 grams of box contains 24 individual chocolates. Sometimes I get them to think a little bit about which one goes on top and which one goes on the bottom, and it really doesn't matter. But if I put grams on top, I've got grams per chocolate. So it's a sensible way to set up my equation, because sometimes that division actually means something. Like if it was meters in seconds, we'd have something profound. But other times it's just a constant of ratio. So 200 over 24 equals 300 over x. We do our cross multiplication. 200x is 24 times 300. We divide by our 200. Divide by our 200. I was a bit naughty now, actually. I tell them to simplify this first. That was very naughty of me, I'm sorry. X is equal to, so 2 into 24 is 12 times by 3 is 36. 36, and then we write a comment anyway, but it's almost leading them up to when we are going to have harder algebra in the questions, and trying to develop algebraic approaches. Grams, so that's cost per gram would be an interesting or useful thing to have. So if I put my pounds in there, it's 80 grams over 15. So that's x over 18. So 15, we go, 5 goes into 80 16 times, is that right? 5 goes into 80, 10, 5, yeah, 16 times over 3 is equal to x over 18. So 16 times 18 is equal to 3x over 3 over 3. So 6 times 16, 32, 96. So yeah, x equals 96, and we've got that there. So it's keeping these methods. It's also good practice of their algebra and mental maths. I never really encourage calculator use, but when they do get to use a calculator, obviously the process is even easier. Same with recipes. So if we've got a certain amount of flour, so we've got grams per cake would be a useful ratio, grams per cake. So we've got 100 grams and make 15 cakes. So that's equal to 60 grams. And how many cakes does that equal? X is equal to 3 times 60, divide by 20, divide by 20, cancel, cancel, 3, x equals 9. So we've got our method and it's kind of working through. So now is where it starts to get a little bit controversial. If the method is really embedded in how students work out ratio, if they spent a long time in algebraic fractions, they're very comfortable with it. A question like this, they might tackle in a non-conventional way, and can I add, probably an easier way as well. If you travel 4 miles in 6 hours, hours, 4 over 6, how far do I travel in 10 hours? X over 10. So you simplify your fraction. X over 10. 20 is equal to 3x, divide by 3, divide by 3. X equals 6 2/3. So I travel 6 2/3. If we do use the more traditional method of just speed, is average speed is total distance traveled over total time taken, we would find that we're getting a multiplier, which could then lead to us trying to work out a decimal or multiplying fractions or other things. So it does work out quite a lot nicer, and it works out nicer as well in density problems. Although, again, probably if I was modelling this to students in a GCSE paper, I would use the speed as distance over time and the density as mass over volume to try and really make those things clear. But I might give them the alternative approach by the side, and some of them do use that, and it is neater. It's just tidier. So I think there's an argument so far that most students who are going to do well at higher GCSE wouldn't have a problem with any of the questions up till now anyway. But this is where we get things where students get things wrong because the method they use is learning a formula. And if they don't learn the formula, or they mix the formula up, or they don't understand the formula, it goes wrong. But if we do sectors, so we'll do the length of this over 2 pi times 6 is equal to 60 over 360. We just have a simple ratio that we simplify. L over 12 pi is equal to 1/6. 6L is 12 pi, divide by 6, divide by 6, L equals 2 pi, and the units would be centimetres, and I'd probably encourage a comment with that as well. And exactly the same for our area of the sector. Area over pi times 6 squared is equal to 60 over 360. So no learning of a formula at all. It's just using a method that's well established and repeated time and time again. Over 36 pi is equal to 1/6. So 6a is equal to 36 pi, divide by 6, divide by 6. And yes, better mathematicians just bring that up there in one step. But we want something that's accessible to everyone. 6 pi centimetres squared. It's notable when we teach this then at A level, it all just moves into radians. So if we had, this was pi by 3, and this is 2 pi, you can see the pi's just cancel. So rather than remember the formulas that the length is r theta and the area is half r squared theta, we're not learning formulas, we're just understanding what we're doing. We're finding a fraction of a whole circle. So it lends itself well to the A-level content. Similar shapes, perfectly. One thing to note is with similar shapes, even if it's just a length one, do get them to go from one triangle to the other, and if necessary, draw them orientated in the correct way. These are, but if I go 3 over x is equal to 10 over 12, so 3 over x is 5 over 6. So 3 times 6 is 5x, divide by 5, divide by 5. X is equal to 3 times 6, 18 over 5 is 3 3/5. Oh, I can't write there because there's a little box on my work, centimeters. So it works really, really nicely with all. We go from one side to the other. 3 over 10 is equal to x over 6. So 18 over 10, the answer will follow through. 18 over 10 is equal to x. So x is 9 over 5. I still don't like using decimals, which is why I really push to use neat methods. So 9 over 5 is 1 4/5 centimeters. Okay, so now we're moving on to similar shapes one again, but we've got an area, and if we taught that already, usually the students are absolutely fine with it and they just immediately do this, which is actually what we want them to do. X over 5 is equal to 18 over 50, and this is exactly what they want, and we work it out with a shape, perhaps a square or something, or something they can work the area out, and we see that it's wrong and it's failed, and we can use a few different shapes to quickly get the idea that this one here is a squared. We were doing this here, so we get to the practice, and if we've done lots of these earlier on in year 8 in particular, we don't get any major problems with them simplifying their fraction. Think of a number, divide by 5, square it. The answer is 9 over 25. X over 5 is 3/5. We mentioned why we don't have to worry about negative things. Good students will just see the answer is 3, but just to keep following a system, other students might prefer to just complete it off and say x is equal to x is equal to 3 centimeters, and we check if it's sensible. So we can do those. We can do them for area. We can do them for volume. System. So we've got the same system for proportion. Now I'm going to, by the side here, give the traditional way of doing this and then our way of doing this, and then you can compare them. It took me a while to be a convert to this, but it really did. So the traditional way to say y is proportional to x. So then we let y equal kx. We sub in our point. 12 is equal to k times 10. We solve the equation, divide by 10, divide by 10. K is 6 over 5, which some students will try and make as a decimal. We then substitute that back into our original formula, 6 over 5x. We then would put in our point y, so y is equal to 4, which is 6 over 5x. We times by 5, 20 is equal to 6x, divide by 6, divide by 6. So x is equal to 10 over 3, and we would have our answer. Quite a lot of work, and I personally believe most people will make a mistake. If we use our simple method of before, and again, I get them in their margin just to put their y in x, just so that it doesn't matter which one's on top, which one's on the bottom, but 12 over 10 is equal to 4 over x. 6 over 5 is 4 over x. So 6x is equal to 4 times 5, divide by 6, divide by 6. X is equal to, cancel, cancel, 10 over 3. And I think it's quite convincing that it's quite a bit less work, and it works very nicely all the time. Students really do, when they learn the method, just find it's absolutely fine. You could say, what about when we have proportional to the square of? Well, it's exactly the same. I get them to write it in the margin just so they're reading it off, but 12 over 2 squared is equal to y over 3 squared. So 12 over 4 is equal to y over 9. 3 is equal to y over 9. Y is equal to 27. So it's much easier than the traditional method. Sometimes it doesn't say what is y when x is. Sometimes it says write an equation in y and x instead of that, which is even easier. 12 over 2 squared is equal to y over x squared. So we get that value 3 is equal to y over x squared. So y is equal to 3x squared. So it works just as easily with all cases. The only issue with teaching this method is when they're taught things in physics and biology where they use this little symbol here, they get lost in biology and physics and chemistry, and they ask us, and we kind of need to translate it into the way that they understand it. And I've added into our year 11 scheme of work a little note on just trying to decode that symbol, because they do need to know that symbol, because sometimes it is used in the exam, but they don't need to really add to it. So the method follows through very neatly with inverse proportion. If you look at the table above, the student should be very confident that these are directly proportional, and they can do 1 over 3 is the same as 2 over 6 is the same as 3 over 9 or 4 over 12, and they understand that this is a fraction. It's the x over y is equal to, let's say, 1 over 3. Or they could do the reciprocals of them both. If you present an inverse proportion, when one gets bigger, the other gets smaller, it doesn't take them very long at all to notice, it's the product of them. So it's xy is equal to 1 times 24. So xy is equal to 24. Y is 24 over x. And then you kind of give them that, oh, sorry, I can't write 24 over x. You get that general rule for students that we divide when it's direct proportion, it's their ratio is the same and their product is the same for inverse proportion. Carry on. So y is inversely proportional to x. So we've got in the bracket here, I would normally get to do yx inversely proportional. So 12 times 2 is equal to y times 3. Solve the equation, cancel, 4, y is equal to 8. So we get there very, very quickly, and if I was to do that by the traditional method, y is proportional to 1 over x, so we let y equals k over x, we sub in our points. 12 is equal to k over 2 times by 2, we get k is 24, so then we get y is 24 over x, we sub in x equals 3, so y is 24 over 3, y is 8. There is no conceivable way that this method is in any way suitable for students if they can do algebraic fractions from an early date and they can solve those equations well. I mean, it's far too lengthy and mistakes will happen. This was one from our previous one, so I'm not going to go right the way through, but just to kind of give the idea that it's the same method used in all these different topics. So every time we practice the method, we get students becoming more confident and happier doing it, and then they solve the equation. So it's all a fraction equals a fraction and solve it. So now we're moving to topics that perhaps traditionally in the old GCSE would have been A-star topics. Why were they A-star topics? Perhaps because students have to manipulate the algebra or not see things. But if you use the idea of a ratio, we just get very quickly that sine A over 10 is equal to sine 63 over 14. We don't even need to teach them the formula, sine A over A, sine B over B. And we don't need to teach them as well, this is the form you do if we know an angle, this is a form we don't. They're used to this and they're used to solving the equation. So if they can get to the first step, they're usually fine. Obviously, this one would need a calculator, so I will carry on. In year 9, our trigonometry comes directly after similar shapes for the exact reason that this angle is a we're looking for a ratio, and the first examples in the scheme of work state to use 30, and then they can spot very quickly that 30 is a ratio of a half. So sine 30 is 5 over x. And again, it's absolutely fine them doing opposite hypotenuse and SOHCAHTOA and all of that, but it's this idea that a fraction is equal to a fraction, and that's how we solve it. This one we could work out as a fraction immediately because we know how to do it. So 5 over x is is equal to 10. And we put some units in with a comment, but the method we've used just puts itself everywhere. Some students like to do this, notably, if it's a number, they just prefer the cross multiplication. If it's just a number, they like to put 1 there, and that's absolutely fine. We kind of hope that as time goes on, they'll no longer need that. Capture, recapture. I think this came across as being a high level problem, but if you're good at solving equations and you can set these up, 30 out of the whole population are marked, and we recapture 5 out of 20. So we solve our equation. 30 times 20 is 5x, divide by 5, divide by 5, cancel, cancel, 4, 120 is x, and we write a comment. So it becomes quite quick and fairly intuitive. Stratified samplings not on the higher GCSE anymore, but they do imply it, and it has come up in an implied case like this where the proportion in a sample needs to be the same. So the words might not be used, but it's there. But we see there's 28 out of 70 is equal to x out of 900. We've got the same thing. 14 goes into 28 twice, 2/5 is x over 900. 2 times 900 is equal to 5x, divide by 5, divide by 5, x is equal to 360. I've cheated there and looked at my answer. I didn't do that very quickly in my head, but I suppose it lends itself well to non-calculator work. I'm coming a bit towards the end. When we first adopted this method, it was discussed and quickly dismissed, but not because it wasn't good, just because we like the method of decimal multipliers. But I used to teach the unitary method of reverse percentages, and I would much prefer to do this now than the unitary method, although I still think decimal multipliers would be my preference. Sorry, after a 20% reduction, so I've got 80% left. So 80 out of 100. The toy is £16, so it costs, what was its initial price? 16 over x. 8 over 10, 4 over 5 is equal to 16 over x. So 4x is equal to 16 times 5, divide by 4, divide by 4, x is equal to 20. So we then write our comment, £20. But we do not use this method now at Queen Mary's. We use the decimal multiplier method. We draw 2 boxes and we say that's times by 0.8. So the final one is 16. So 16 divide by 0.8 will give us our answer directly. So that is our preferable method, but it would work, and I would probably say it's tempting to use this method for that as well, because it would work and it's just another reaffirmation of it. So the things that I was hoping to do is to offer an alternative approach to teaching lots of topics. I've shown my terrible handwriting and my modelling, but hopefully you see how I might explain those to a class, and maybe that's something that you liked, or maybe actually you could think, that's something I won't do myself, and that's also a positive thing to come out of it. And this idea that when we have a method, we try and use and practice that method in as many different topics as we can, so we're consistent and the students learn a consistent approach.